Good morning. They're ready. They're ready. You're ready? It looks like I know we're all thinking about spring break. It looks like about 2/3 of us have already grasped that idea right away. No point in waiting. No point in waiting till Thursday. Spring break is now, I guess, if you want. Okay. Well, so let's see. Coming around. Homeworks are coming around. Okay, so there's in the folders there's homeworks, old homeworks, I think homework 4, and then there's homework 5 coming back around in these folders. And then there's one page for discussion today. We hope for some clarity. Somehow it seems like unless we have some influx of hordes of influx, we would have just the right size for discussion. That's not maybe what you planned on, active discussion, but we certainly we're approaching the size for active discussion. So the problems are on the Poisson process. The outline, the procedure here may seem slightly schizophrenic in the sense that the whole subject may seem like that. But anyway, I started this section doing some of Chapter 5. Then the second stuff is some of Chapter 6. And now I'm going back and doing some more Chapter 5, and then I'm going to do some more Chapter 6. And the second midterm is going to cover Chapters 5 and 6. But there's sort of an easy story to Chapter 5 and an easy story to Chapter 6, and then there's some harder parts. So my general thought was to start with the easy stuff in 5, the easy stuff in 6, and then the harder stuff in 5 and the harder stuff in 6. That's my thought process. Actually, all the stuff, the homework and stuff up to the midterm, the homework up to the midterm is online, so you can judge for yourself. I mean, the midterms aimed at March 31st on Thursday, you can judge how to, there's a homework assignment starting today, obviously not due in the middle of the break, but due a week from Thursday, so you have time before the break and time after the break to do it. But it's not totally crazy. It's just sort of, there's a week break, but not 2 weeks break in the homework. Yeah, so there's 3 things coming around. Homeworks in this one-page handout for today. So this is these problems on the Geiger counter, an ATM, and typographical errors. And then Thursday, I'm going to talk about some stuff related to some of my own papers which have to do with applying things to queues. So it has to do with queuing, but it has to do with the Poisson process. So some of that stuff is online. So this was online. As I sent you an email, you could have looked at this. Maybe many of you looked at it and decided that, those who aren't here, they looked at it and decided that, yeah, that's totally clear and they don't need to be here. But anyway, whatever. So we're going to, talk about a little Geiger counter problem, which is just a warm-up. The ATM problems, withdrawing money from the ATM, is a little more interesting because you're not only thinking of the times of the withdrawals like a Poisson process, but the people are withdrawing random amounts of money each time they come. So you're thinking, what's the total amount of money withdrawn? That's this issue. And then the typographical errors is actually, I think, kind of interesting. So you have some book or article, you have a book, say, and you have 2 proofreaders, not just one. And one proofreader finds a bunch of errors, and another second proofreader finds a bunch of errors. And then, so some of the errors are in common, right? Some of the errors they find are the same errors, and some aren't. So then you try to figure out, on the basis of that, instead of just having one proofreader, you have 2. And if you have 2, and they find some are the same and some not the same, you can now estimate how many errors are there, total, unfound. Right? You could get an idea of this. And moreover, you could estimate, suppose you hired a third proofreader, how would you do? And actually, this is kind of a nice thing. This is, again, the point, I think, of this example we're getting to, that last one, is something where actually it's kind of a reasonable question and not totally obvious, although the answer would be, I think, if you didn't have this course, you ought to be able to figure out the estimate for yourself, because it's reasonable. But the course all falls into it, and it actually could evaluate the distributions of things. How likely would those estimates, what's going on? Okay, that's an overview. So let's start with the Geiger counter. So these problems there's a sheet coming around, so you should have this sheet. There's many more copies than we need. There might be, everybody could have 3 or 4 copies of this page. Okay, so let's start with the Geiger counter. Pulses arrive at a Geiger counter according to a Poisson process at a rate of lambda equals 3 arrivals per minute. So you're in some background environment with your Geiger counter, and it's click and then click. Not much is happening. I mean, you're not going up to the radioactive source. Click, 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 click. Right? Okay, that's not happening yet. But the source is somehow, and this actually, the physics of the thing actually makes it so a Poisson process is the right thing, roughly, of what goes on in the Geiger counter. Just a question of what the rate is, which is the issue. And then probably you don't care a whole lot about the stochastic part, right? So it's kind of a stupid question. But anyway, you could be, in some physics things could be like this, and you might care. Okay, so you have this Geiger counter, and you assume that pulses arrive at a rate of 3 per minute. And then suppose that each arriving pulse has probability 2/3 of being recorded. Then so we have Geiger counter. So this is 1, Geiger counter. And then we have x of t, which is the number of recorded counts in a time t, from 0 to t. What's the probability that there's exactly 7 recorded counts in 7 minutes? So you're looking at probability x of t equals 7. Did I say that right? I probably got it missed. 7 counts in a 4-minute period, so that's t equals 4, right? So this is just a Poisson, and the thing to remember about the Poisson process is the mean is the intensity lambda times time. So this thing is, in general, this, where the lambda t is the mean of the Poisson. So it's proportional to the time. So in this case, the lambda originally was 3, but we have to multiply by 2/3 because 3 was the rate of the pulses and 2/3 was the probability of being recorded. So this lambda is 2 and t is 4, so that's e to the minus 8, 8 to the 7, 7 factorial. In other words, lambda t is 2 times 4 equals 8. Right? So all you're doing is a Poisson process. The mean is the rate lambda times time. So what is the mean of this? What is the mean of the expected value of x of 4, and what is the variance of x of 4? Well, the mean and variance of a Poisson random variable is just lambda t. So it's 8. That would be good cause to not show up. This problem is pretty easy, okay? This is just to remember. You want to remember the Poisson distribution for a Poisson process. You want to remember that this mean is lambda t, and then you want to compute lambda t appropriately. Okay, let's move on. The other two problems are more interesting. This is the warm-up problem. The ATM machine is a little more interesting. So there's something going on. We'll turn to the ATM machine. Okay, second problem. Now, let's see. Okay, well, there's something. Customers arrive at an automated teller machine at the times of a Poisson process at a rate of 10 per hour. Suppose that the amount of money withdrawn on each transaction has a mean of $30 and a standard deviation of $20. Find the mean and variance of the total amount of dollars withdrawn in 8 hours. And I guess the missing question that should be there is, what's the approximate probability distribution of the amount of money withdrawn in that time? So the time interval is 10 hours. Now, this is a little bit, this could be more complicated. You could have that the people coming to this ATM machine, they could see somebody else using it and go away, right? You could have a queue. They could be waiting in line. Sort of none of that's there. We're just assuming the people come at this rate and they're going to eventually get served. They might have to wait, but they're going to stay once they come. So that they may wait or not wait, but that's not a factor. They're all going to they're going to come at some time, and if they wait, they'll take the money out. And the waiting is inconsequential. Somehow the time period this is 10 per hour, and we're thinking the waiting time's a small-ish, not an issue. Waiting time's a minute or two or something. It's not an issue. So we have lambda is 10 per hour. And then the money. So we might have money. The ith person is the dollars withdrawn. And we're thinking simply that the people arrive at this rate, and all these people are taking money out. They're not doing anything else. So they're all taking money out, and the yi dollars withdrawn by person I. And then the arrival process is Poisson. So let's see, n of t is arrivals. Arrivals in this interval 0t. And it's got this rate. Okay, so then what we want to do is look at mean and variance and distribution of the total number of dollars withdrawn in 8 hours. Okay, so we're actually going to define a new stochastic process here because we're going to talk about the dollars. So in this case, we're going to let x of t, this is the object we're going to look at, and this is a random sum. We're going to sum up all these random dollars for all the people up to the random number of arrivals. And that's going to be the total dollars, right? And actually, both n of t is a stochastic process, a function of t, and so is this total dollars, a function of t. So we've got a stochastic process that we could look at. And this stochastic process is called a compound Poisson process. And this is one of the topics at the end of chapter 5. So this is things you're coming to in this next assignment, to look at a compound Poisson process, which is, now, the assumptions are that these dollars withdrawn are independent and identically distributed. All the people, the amounts withdrawn have the same distribution for all the people, and different people are independent and identically distributed. We haven't said what the distribution is, but it's something or other. With mean and variance we've specified. So we specified that the mean, say, for each person was $30, and the standard deviation was $20. So there's some distribution about how much money each person takes out, but the mean is $30 and the standard deviation is $20. Now, I don't know, before we just calculate the answer and so forth, which is, I guess, what I intend to do, I guess the thing I want to point out is that this new stochastic process, which is counting the amount of money withdrawn, is actually also a very special stochastic process and has lots of nice properties. The thing to remember about this Poisson process, which is this n of t, is it's got independent increments. And these yi's are also independent and identically distributed. So therefore, this process, x of t, is going to have independent increments. In other words, we can look at this as x of t could be, say, we divide 0t into any number of equal intervals. So you can think of dividing it up into n equally spaced intervals. Right, so you'd have x3t over n minus x2t over n, and so forth, all the way down to xt minus xn minus 1 over nt, right? So all I'm doing is taking x of t is the sum of what it would be in each of these separate intervals, right? I could look at that. And these are and this one is and so forth, right? This is the sum of all these y's between up to this. And this is the sum of the y's after that to this, right? So the index is the count. This is the Poisson process, counting the number of arrivals in this interval, and this is the number of arrivals in this other interval, and then we have these sums of these independent things. So the Poisson numbers are totally independent because they're independent increments. And these random variables in the different intervals are independent and have nothing to do with the Poisson process. So you directly see that because these are assumed to be independent and identically distributed, and because the Poisson process has independent increments and independent and identically distributed increments, this divides up into n independent and identically distributed random variables. We've made these intervals of equal length. The dollar values in each of these intervals has the same distribution, and they're independent. That tells you see right away that this x of t can be, if t is not too small, this in any case can be represented as the sum of n independent and identically distributed random variables. So therefore, you would be inclined to think I could apply the central limit theorem and it's going to be approximately normal. And that's what you expect, as long as the numbers aren't too small. So the distribution of x of t should be approximately normal. The question then is, given that, all you need to know more is what's the mean and variance to know the distribution. So then you could be asking questions, what's the probability that the amount of money withdrawn in some period was greater, than some amount that the cash the machine's stuffed with, something, right? You want to know how how many dollar bills need to be in the machine or something. You could figure that out. Okay, so the normal distribution. But now we want the mean and variance, or the mean and the mean and variance, and the mean and standard deviation. So you want this. You want, let's just say this. You want the expected value, and that's just the expected value of this. Now, this thing looks messy, right? Here we got this expected value, and there's this random thing here and this random thing here. It looks messy. Okay? So, in your mind, is it clear? It should be clear what you do to proceed at this point. There's sort of a standard strategy of which this is one instance of how to proceed the next step. And the standard thing here is to divide and conquer. Simplify this. Condition on this. Condition and uncondition. Whatever you're doing. So now this is a key strategy that we've been using in a lot of the problems. If you have too much complexity, you condition on one thing and uncondition. So that's exactly what we're doing here. So we write this we look at this and we condition that n of t equals n, and then we multiply by the probability n of t equals n, and we sum on n. Right? We condition on it. We want this, so we condition on this, multiply by the probability, and sum. So this is now simplifying. Now this thing, what does this look like? This inside thing, once we've made this n, you're looking at this. Once you've conditioned on n of t as n, this is now that two randomnesses are gone away. There's only one randomness. Right? So the problem's simple. I mean, that one little step, the one little step of conditioning makes the thing easy. If you just look at this head on, you say, I mean, actually it's got a simple answer for the mean, and it's just what you think. It's this expected value this times the expected value of that. But when you get to the second moment, you're going to screw up if that's all you see, because it's not easy. The second moment requires this thinking. So when you do this, you're going to see that that's continuing. This is n times the expected value of y1, their IID. And sure enough, that's obviously which should be entirely what you'd expect. If you said, what's this straight away, what should this be? Sum of a random number, it should be the expected number times this expected thing. That's sort of obviously what it should be. So I guess you could start by saying, oh, look at this, what should it be? Okay, totally reasonable. This expected value times this expected value, that's the answer. But this step is actually going slower, and then writing it down, when you factor this constant out, you've just got the definition of the expected value, so you've got this. Right? So it's obvious this is the answer. Sort of, you think it's the answer at least. Things are not always what they seem. And when you do the derivation, you get this. So it should be obvious from straight away that this expected value would be the expected value of this times the expected value of that, because it's this expected value times this expected number of terms. And that's what we get. Totally, so that's consistent. I mean, there's no surprise. The tricky part is calculating the variance. You now want to know the variance of x of t. Okay, and that's not going to be, oh, the variance of this times the variance of that, or whatever thing you're going to make up, just isn't it, right? It's not going to come out of your ear, some simple answer. So that then you want to think about this process, and that's what we're going to do. We're going to imitate that same process. Let's see, so maybe we'll do it here. We all have our homeworks back, and we have this one page. Nice little tune. Nice little tune. Okay. Now, we want variance. Now, the point that's a little tricky here is actually this story is easy to do with the second moment, but not for the variance directly. Because the second moment, I just put an expectation in here, and it's the same thing. So I'm going to start doing this and do this. The second moment. And this thing's going to go through, and then I'm going to, in the end, to compute the variance. So I'm doing this, and this thing looks... And I've done the same thing as before. I condition and uncondition and wait and do this. Now, when I do this, this n of t makes this n. So I have sum of n So far it's the same reasoning. I just go through and I've got, the reason is I'm just doing an expectation. A variance is complicated because it's not an expectation. It's a bunch, something else. So when I do this expectation, I'm doing expectation and I condition and uncondition. So I want to do the same thing, which I can do with any other expectation if I put a function in here. I don't do the variance directly because it's not directly an expectation of a function. It's a difference of the second moment minus the square of the first moment. So I can do this directly. Now then, what I need to do is I need to do a little arithmetic and so forth to make sure to get this manageable, because this is not quite what I want. This thing here, this is fine. This is inside here. This is just y. The only randomness here is y, and they're all IID. But this is the second moment of the sum. So now I'm going to actually go, and I know when I'm looking at this, I know that the mean is n times this. And the variance is n times the variance of y1. But I want the second moment of the sum, right? So all I need to do is remember the definition of the variance in the second moment. This thing is, the second moment is the variance. Well, it's the variance of this thing plus the expected value of this sum squared. Right? That's this thing. I first used the fact that the expected value of this second moment is the variance plus the mean squared. Because I know what the mean and variance are going to be. So then I look here, the variance is n times the variance of y1, and this is the mean squared. So this is n times the expected value of y1 squared. Right? That's all inside. So this part of the problem is really very nice in terms of basic probability and illustrating, basic things about the formulas for the mean and the variance and the second moment and how they're all related, and you just condition and uncondition. So the derivation is sort of very natural story that flows forth here when you do this. Okay, so let me erase this one. This would be a great time for a penetrating question that would clear this up if there's any confusion for others. If there's confusion here, this thing should be, we've got this, it's the second moment, and I do that because it's some sort of expectation. I compute it by conditioning and waiting unconditioning. Then I've got this sitting here, and when I condition, the n of t is replaced by n, but this thing, as it came from here, is the second moment. And since it's the second moment, I represent it as the variance plus the mean squared, and I can calculate those two. So it turns out that at this stage, I needed the second moment. I couldn't work with the variance directly. And over here, I know how to do the mean and variance, but not the second moment. So I go the other way, and I can put it in terms of the variance and the mean. So I'm conveniently going from variance to second moment, and over here from second moment to mean and variance. And so now I have this in terms of mean and variance, and this is just two sums, but there's an n here and an n squared here. Right? So looking at this thing, let me write it down here. To rewrite this thing, here's n, and then we have n variance y1. I'm breaking it into two sums. And the other one is so I just split these things into two terms. I think I'm going along okay. Now this part's a constant. These parts are constants, can be moved outside. So this is and this one is right? This is just this. In other words, variance y1 is pulled out, and this is the mean of n of t. The mean squared is pulled out, and this is the second moment of n of t, just directly, by definition. So now we want this, the variance. Well, that's this minus the square of the mean. So it's this thing up above minus the square of the mean, which we know was this. Right? So the variance of x of t is this second moment minus the square of the mean. So again, we're going back and forth. We're going to get the variance in terms of the second moment. And here we've got all this, and we've got this. So we have to take from these two and subtract this mean squared. Okay. Then when we do that, let's just see what we've got. Now, actually, this process that I'm going through is, I suppose, not really entirely necessary. If you thought you could shortcut this by, you will probably, most of you probably will shortcut all of this by writing this final answer down on your piece of paper, right? Or knowing where it is in the book, that the formula sits there in the book. Because when you do this, you're going to get variance of x of t equals. Now, the thing to observe is this is fine, so we get expected value of n of t times variance of y1. That's this first term here. Now, this is kind of interesting. Notice that this, we've got the variance, so we have to subtract this term here, right? So we've got the mean squared times the second moment minus the square of the mean. Just these two terms. So they can be combined into plus, right? Did I get this right? This squared, and then this is, am I messing up here? Variance n of t. Because the mean of y1 squared, and then the second moment minus the square of the mean is the variance. Now this is this x of t, right? This is x of t. Now actually, we're now in chapter 7. This also covers more general cases because I haven't really used the fact that this is a Poisson process yet. This n of t. I haven't used that. So it's going to apply when it's a renewal process. But anyway, this formula doesn't assume, so far we've got the answer, but we haven't assumed it's Poisson. So if you assume it's Poisson, this becomes lambda t, and this becomes lambda t. Now, this is Poisson process. If I make n of t a Poisson process, the mean is lambda t and the variance is lambda t. Right? And now I've got lambda t and I can group terms. So I've got lambda t. This is a little strange, right? Because this part, the lambda t is the same in both terms, and I have the variance plus the square of the mean. That's the second moment. This doesn't exactly make intuitive sense, right? This is saying that let me put a couple of here. The variance of this random sum, the variance of the random sum is this Poisson mean times the second moment of the y1. It's a little complicated. If you didn't have Poisson, you'd have this formula at the top, which is more general. If you knew what to put in for these. Now, this is what I'm getting. What I'm getting to is your one page may have this. Okay? That's the answer. That's the formula. So at the ATM machine, you need to know lambda t, the rate, the time interval, and then this is the random variable, the dollar withdrawn at every time in its second moment. So if we were told, as we were here, if I remember to look at my sheet, the expected value of y1 and the standard deviation of y1 in dollars was $30. And the standard deviation is $20. So we want the second moment. So again, we're now wizards of going from mean, second moment, variance, back and forth, right? You do it about 10 times in this example, right? So we want the second moment, we have this. So the second moment is the variance of y1 plus the mean squared. And so the variance of y1 is the square of the 20 squared, square of the standard deviation, and the mean squared is square of 30. So 400 plus 900 equals 1,300. What's missing? Something I'm not doing right. But I haven't multiplied by lambda t yet. Yeah, lambda t. So lambda t, yeah, I'm looking at, I have my cheat sheet. I have the whole answers here. It doesn't look right, so that helps. That helps a lot. Lambda t, 80. So lambda t is, what was this story again? 10 per hour and 8 hours. So 10 times 8 equals 80. And then you have the variance equals 80 times 1,300, which turns out to be 104,000. And now you see, well, that's about 310 is the standard deviation, right? 322, actually. Okay. What's the mean? The mean is 80 times 30. So the mean was, lambda t is 80 times 30 is, wait, am I getting this right? 2,400. Is that what I've got here? Yeah. So this is the mean dollar amount during that 8-hour time period is $2,400, and the standard deviation is 322. So if you were asked what's the probability that it was more than 4,000, well, 4,000 would be 1,600. It would be 5 standard deviations above the mean. not very likely, right? So you can assume this is saying it's this mean and this standard deviation. To compute probabilities of things, you can use normal approximation. Okay? Okay, I'm ready to leave the ATM machine and look at typographical errors. Okay? This would be a good point for any kind of question. We need your alertness. The problems are ramping up in difficulty. This one was reasonably hard. The first one was trivial. The next one's kind of conceptually more challenging, but actually reasonable, I think. Okay, so I want to go to typographical errors. Now, this is, let's see. Let's see what the problem says. Suppose that the number of typographical errors in a new text is Poisson distributed with mean lambda. Now suppose that two proofreaders independently read the text. Suppose that each error is independently found by proofreader I with probability pi, and then there's a, so let's go back further. So I want to go back further. Maybe this is all right. Start here. Is that you actually could make a model of how the errors appear, which leads you to thinking of it as being a Poisson random variable. So I want to start with that as why that's a natural model. So you might think that you have a book. You have a book, and it's 100 pages, and on each page there's 100 lines per page, and there's 100 characters per line as a rough, it's a little bit, usually 80s may be better. So that's 10 to the 6th characters. And your model might be that each character, this is of course a little bit extreme, but the simplified model is each character is an error, in error, maybe even the blanks for what simplicity. Each character is an error with a small probability, independent of everything else, right? That's, of course, an idealized model that gives you a reference case, but that's a natural thing. So you have each characters in error with a very small probability, and there are 1,000,000 characters. So n is big, and this little probability, we could call it epsilon, is the probability. Then lambda, the expected number of errors, is n epsilon, and the actual number of errors would be binomial with parameters n and epsilon. But it is approximately Poisson with a fantastic Poisson approximation with mean lambda, which is the 10 to the 6 times whatever epsilon is, which we don't need to know in our case. But we're going to have lambda, but we're not going to know lambda. This is just the first to say it makes sense to model the number of errors in the book as Poisson, or in anything that you're looking at by that kind of reasoning. So it's reasonable that the number of errors in the book is random with Poisson distribution with some mean lambda, whatever that is. That's the starting point. Now, being clever, the author or whoever wants to check the book is being clever. The cleverness, again, is that they're going to have two proofreaders who have some. Now, again, a simple model. Each proofreader is going to find an error with some probability. If there's an error there, you're going to find it with some probability, each error independently, and so forth, in a simple model, right? So it's sort of a natural thing. There's a bunch of errors that are there, and each one's going to be found with a certain probability. So you have proofreader 1 is going to find an error, with some probability P1, and P2 find error. This is reader 1 and reader 2. And there's a lambda. the rate of errors, mean number of errors. So we have the errors, our model is the errors are Poisson distributed with some mean lambda. And each proofreader is a kind of binomial error finder with finding these probabilities, of finding it. However, in practice, we don't know any of these things. We don't know lambda, and we don't know these probabilities. We don't know how good the proofreaders are. However, what we want to do is use the fact that we've got two proofreaders to estimate all this stuff. So we want to know how many errors are uncovered, not found. This might be more to the point, but also less fitting if this was computer code. And you said you had somebody, you're trying to debug it. And you kind of went through and you found how many, this is kind of thing is used, but it's the model is a much more question of code is more complex structured and things are not totally independent by any means. But you could use this model as a rough way of figuring out bugs, how they're being found by different people studying this stuff. And what if you think, well, they're going to go through this, and you could have, there's some bugs where that doesn't mean character by character, but somehow there's some number of bugs in this large set of code, and you have two people go through the code and find the stuff, and they've identified it. And so whatever it is, errors some way, there's some rate. Now you don't have to define it precisely as character by character, but you think of independent bugs, and the same story goes through. There are some probabilities for finding them and how many are there and whatever. And then you want to look at what they find. So this is model parameters, but unknown. And then we're going to observe x1, x2, x3. Well, we're going to observe these. Errors found by 1 and not 2. Errors found by 2 but not 1. And errors found by both. And then here is errors not found. And we really want to know the expected value of the errors not found. Maybe. That's what we want to know, how much more is left there. Okay, well, let's go to... Now, actually, let's think about this. This problem has a way of degenerating into complicated nitty-gritty that is going to require that I need the cheat sheet to follow out what the answer is. And yet, conceptually, it's simple. So the main, I want to kind of, instead of just doing it in front of you, and you're going to sink into this the detailed morass, is just to see that it's conceptually simple. And that is that we're going to observe these three random variables and not this, but when these four random variables are easy to characterize their distribution. And that's going to be the key. So what's happening? You have an error. So think of the errors. Well, okay, let's have the errors here. Here are the errors. If we think of a Poisson process, the errors are spread through a single line of text. So here are the errors. This is the errors. And then we have proofreader 1 and proofreader 2. So proofreader 1 finds these with P1. Finds this one and this one. Proofreader 2 finds this one also. So this is with probability P2. So there's a Poisson process through the list of characters where errors are occurring with the total mean lambda. Each one is occurring with some small rate, but the overall mean is lambda. But there's this Poisson process. When we find the errors, that's a thinning of the original Poisson process with this P1. With probability, each of these errors is found. So it's a new Poisson process, and this is a different Poisson process. And you can then thin it to, I guess if you thin it further to which is both, you're thinking you have these cases. You're thinning 1, not 2, 2, not 1, 1 and 2, neither, right? And this occurs with probability P1, 1 minus P2. Probability P2, 1 minus P1. Probability P1, P2. Probability 1 minus P1, 1 minus P2, right? So that each error, 1 finds but not 2 with this probability, 2 finds not 1 with this probability, and so forth. So these are the probabilities for each error, and the processes that lead to these random variables are these become 4 independent Poisson variables. So the bottom line of this picture, we get rid of the ATM. X1 is distributed as Poisson lambda P1, 1 minus P2. X2 is Poisson lambda P2, 1 minus P1. X3 is Poisson lambda P1, P2. That's found by both. And X4 is Poisson lambda 1 minus P1, 1 minus P2. Neither. This is the neither. Neither and both. So the expected values are precisely those numbers. Right? So this is just this is the easy part. This is the kind of if you have all this model, if the total number of errors is Poisson and we split them into these 4 cases, there are 4 independent Poisson random variables with those means. So actually, we observe 3 of the 4 Poisson random variables which have these means. So remember what, let me put this here. So the idea is this. We observe x1, x2, x3. We then estimate the expected value of x1 by x1, the expected value of x2 by x2, the expected value of x3 by x3. In other words, we actually observe the actual random variables. We don't know this theory in the background. We observe the number found by 1 but not 2, the number found by 2 but not 1, and the number found by both. So we observe 3 things, and we estimate these means by we estimate the actual means by the observed values, which makes sense. We're looking at a Poisson variable, and it's got some mean, and if it's a whole book, it's going to be a big number. So if the mean's big, its variance is the same, the standard deviation is going to be small. So the distribution, there's going to be some large number of things, but this mean is, the standard deviation is going to be relatively small if this mean is not too small. So you're actually having a pretty good estimate of the mean by the actual value. In other words, if you see 100, You'd say the mean's going to be 100, but the variance would be 100, and it would actually be probably 100 plus or minus 10, right? But you'd estimate the mean to be 100. If you observed that proofreader 1 and if there were of the errors found by 1 but not 2 was 100, so x1 was 100, you would estimate that the expected value of x1 was 100. So you're actually doing some statistics here. You observe the x's and you estimate the unknown means by the observed values directly. This is the statistics problem lurking in the background that confuses this, because it's not just straightforward probability. You're not starting with, this is the model, what's the probability? You're actually, in the real world, observing how many errors each of these people find. And you observe x1, x2, x3. And you naturally estimate the means by those observed values. Now, conceptually, everything, you are in business. The question is, what should be your estimates of lambda and P1 and P2? What's going on here? What don't we know? We don't know the model. We don't know lambda, we don't know P1, and we don't know P2, right? There are three things we don't know, three parameters. We don't know the overall mean number of errors, and we don't know the probabilities of the two proofreaders. So there's three unknowns. Yeah. Yes. We have three equations, and we have three unknowns. That part, up to here, what I'm trying to emphasize is conceptually, that's it. That's the conceptual thing before you get into the arithmetic nonsense. There's three equations in three unknowns. Here's three equations in three unknowns, right here, right? Well, we need these expected values, but we estimate those expected values by the observed values we see. Okay, now the point of this approach is that when you go to solve those equations, it gets messy, but it's not, it's not actually hard. It's just, it's a little messy, and you don't see the formula. When you solve the thing, it's enough of all these variables, it's a little awkward. And so it's no longer, conceptually, three equations and three unknowns, there's going to be a solution, everything's fine. And you'll find it, okay? That's the main thing to observe, not, certainly this problem is very narrow and specific. So the general idea is interesting to, would you memorize, in this case, these formulas? No, I wouldn't think so. I mean, it's unlike the ATM. The ATM machine example was really basic. That compound Poisson is really basic. This is kind of a weird problem. But anyway, so knowing that, let me now get assistance. Okay, there's a bunch of questions here. So I guess this one was good. This is helping you along to thinking about the ratio of those means. So you say, well, the ratios of those means is going to simplify x1 to x3, I guess. It's better if we do this. Because if we compare these two, both the lambdas and the P1s go away, right? And if we compare x2 to x3, this is 1 minus P1 over P1. So this is going to get us directly, if you look at this, you're going to say x1 over x3 is an estimate of 1 minus P2, let's say this. The exact equation that we've got, the nice thing is this approach, what we just did is we had three equations and three unknowns. This particular equation gives us one equation and one unknown, right? That simplifies things, right? Okay, that just happens to be that way in this case, that there's one equation and one unknown. Okay, that's a little bit better than three equations and three unknowns. So there's this, but then this thing is just replaced by this, the things you're estimating, and then this is the estimate, where the estimate is obtained by just replacing the values by their estimates. And you solve for it. And what do you get? Okay, so P2 hat equals, I guess, x3 over x1 plus x3. Now, let's see if this makes sense. The probability for, this is probably what you'd get to, again, this is reasonable that you'd get here right away. The estimate for a proofreader 2's probability of success is the number of errors they both found divided by the number of errors that one found, either separately or together, right? So you say, well, look at all the errors found by one, which I observe. That's these two. These are found by one, but not two, and both. So if I look at all the errors found by proofreader 1, and I look at the fraction that are found by both, that's an estimate of what 2 found, probability. And the same dual thing for 1. So this is what you would, admittedly, you could reasonably laser right there. Okay, right? So it's consistent with your intuition. I think you would see that if I only look at what, I mean, you're thinking, you got to think about what you see. You only see what 1 identified but not 2, and 2 identified but not 1 in both. So the reference case ought to be what 1 found, and what they both found over what 1 found is an estimate for 2's probability, and vice versa for 3. Okay, then a little messier, I don't know, this is, the next part's a little harder, but let's see. So then you get, this part is less obvious to me, but you get this. No, I don't know. I haven't a clue. But maybe there must be something there. I didn't think hard enough. I'm just writing this is the answer to the lambda. I don't know what what does that mean? What does that mean? That's just consistent with the same reasoning. I'm saying this part is really obvious, but the lambda part's not so clear. So you're actually estimating here what you think the total number of errors, and this x4 is going to be the x4 estimate. Well, the estimate of this is going to be lambda hat minus right. In other words, you're going to take the lambda hat and subtract the estimates for the 3 things. And that's going to give what's left over. And then these are, did I say what, and I guess you can get all of this. I mean, I may be leaving out a step here. So here's a bunch of numbers. I guess this was one of these things. Let's see, have we done? Okay, you proceed for, it's good to go to E. So I guess 60, 30, 40. So, x1, 60, x2, 30, x3, 40. So you think, well, oh, the P1 is both 40 over, or P1 would be both 2 but not 1. So P1 is 2 but not both 40 over 2, which would be 30 plus 40 equals 4/7, and so forth. Then you go and you get to the x4 hat comes to be from, you do the stuff in here and you get 45 from all this stuff, combining all this stuff, I guess, right? I mean, this is, okay, so you plug all this stuff and you see what the you have these observed, 1 but not 2, 2 but not 1, both those errors, and then you estimate that the number of errors left is 45. And you change the parameters a lot, and you could actually find cases where the number left looks huge, right? I mean, if they each found a lot, but there was no intersection, you think your manuscript must, if the interception, if X1 and X2 are big and X3 is small, then there must be a lot more there. It's sort of like magnified, right? Because that's, and that's what you get. Where in this case, that isn't true, and what's left, this is a fairly big overlap, and what's left is not too much. But you could have what's left is, 4,000 or something, right, as an estimate, depending on the parameters. So you actually could distinguish between cases where there's hardly anything left, like 4 or 5, to ones where the same order, 40, 50, or where there are thousands, right, easily from this kind of analysis. Yeah, it's just stretching the arm at this point. Okay. These solutions will be online. So this business of all these details, you can see it slowly. But I mean, the main thing is there's some statistics, right? You're thinking this is combining statistical thinking in a very basic level with the probability model. Because you have to think, but this is very natural though, because there isn't a lot to look at. I mean, you could start looking at the text specifically, but maybe that's not much point. So it's totally reasonable that you look at the total errors, the X1, X2, and X3 is the natural data to look at to estimate X4 and so forth and all this stuff. So it's totally, seems reasonable. Okay, well, it's this, in a slower form, in a written form, it will be online with all the steps there and the formulas, so you can see it slowly, and you think, oh, that's what he meant. What was that? All that babbling was about. Okay, that's what it is. Okay, it'll be it'll be there. Of course, that may not be clear either. I'm sorry. I don't know. That's not clear either. That it's beyond me. But you can ask. You can always ask us. You can send an email, or whatever. Anyway, okay. We segue into lunch. Right, lunch. Yeah, it's time to stop.